Okay, there we go.
Okay, so hello everyone. Thank you for being here today. Today's speaker is Juan Kuntz, who is a postdoc at Warwick, and he'll talk about product-form estimators. Juan, please go ahead.
Okay, thank you, Jure, both for the introduction and the invitation to give this talk. It's a nice change from my usual, which is probably lurking in the background of these calls. For those of you that don't know me, as Jure said, I'm Juan. I'm a postdoc in the department working with Adam. I've been around for about a year, in as much as any of us are around these days. And today I'm going to talk about some work I've been doing since then, both with Francesca and with Adam. And it's some work on a subject that we didn't really set out to work on, per se. It's something that we stumbled across while looking at these generalizations of sequential Monte Carlo that have been proposed in the literature. Now, before anyone gets too alarmed, I'm not actually going to talk about SMC or anything in any way complicated. I'm going to talk about these very simple things that we call product form estimators. There's something that when we started to look at them, we struggled to locate them in the literature for quite a while. By now, we've found them, at least in some form, and I'll elaborate on that later. What else? Before I start, I should mention that we have a preprint up on archive. We posted a couple months ago. So if you'd like any further information on anything that I say today, or you'd like to have a look at the proofs of the results I give, or check out the related literature, that's the place to go. So let's actually get started. I promise simple, and I can't think of a simpler starting point than the kind of basic Monte Carlo setting, in which we're given some target distribution mu on some underlying space and some real value function phi on the space, and we're tasked to compute this integral here, right? The average of phi with respect to mu. Now, if you open any sort of introductory text on Monte Carlo, probably the first thing you'll come across is kind of the IID estimator, right? That involves drawing n IID samples, x1 to xn, from our target and computing the relevant sample average, right? And then these books or notes will tell you that this is an operation justified by the law of large numbers, which tells us that this is a consistent estimator for our average of interest. So if we draw enough samples, if we choose a large enough n, this will be close to our actual target. And at that point, you hit what I think is probably one of the most hideous questions in Monte Carlo, which is, okay, what does this large n mean? How many samples do I actually need to draw in practice? So most of these texts will start by giving you an answer of this type, right? They will say, by the central limit theorem and the variance expressions for the IID estimator and a host of other results, our estimation error is inversely proportional to the square root of the number of samples that we draw. So what we need to do is we need to pick an n that is inversely proportional to the square of the error that we want in our estimates. Now, this answer is informative in some ways. It tells you things like if you want to increase the accuracy of your estimates tenfold, you need to increase the number of samples that you generate 100-fold, right? But it's also not a very good answer because it doesn't really feature in it at all the actual target distribution or the integrand that you care about. And in practice, the IID estimator works very well for some mu's and some phi's and works terribly for others, right? In particular, there's no mention of the dimension of the underlying space on which mu and phi are defined. And typically, as you know, in practice, this matters a lot, right? A lot of these texts, not a lot, but some of these texts, because of that, they'll make a sentence, they'll say something of the form that Monte Carlo overcomes the curse of dimensionality. And I don't think I need to convince anyone here how ridiculous of a sentence this is, right? In practice, if we go up in dimension, our estimators start to struggle, and past a certain point, we typically can't get them to work. So here's a slightly better answer that a lot of these texts will get to at some point, and they'll do an analysis of this type. They'll say, okay, say you want a relative error of epsilon, which means an absolute error of epsilon times the magnitude of your average of interest. Now, because the IID estimator is unbiased, you should pick an n such that the standard deviation of the estimator is the error that you want, right? or maybe half the error, or 1/3 the error, something like this. Right? And then you proceed by writing down the expressions for the standard deviation, which is inversely proportional with the square root of samples, and the proportionality constant is just the standard deviation of phi with respect to mu. Right? And then if you combine these two things together, you find that the number of samples you need to achieve a relative error of epsilon is inversely proportional with epsilon squared, and the proportionality constant is this coefficient of variation squared, which is just the standard deviation of phi with respect to mu, normalized by the magnitude of the average of interest. So this question of how large do I need to pick n just becomes how large is this coefficient of variation. And I found it a little bit shocking how easy it is to build examples in which this coefficient of variation grows ridiculously quickly with the dimension, and in such a way that the number of samples that you would need for the IID estimator to give you any sort of reasonable estimate quickly gets out of hand, and it becomes an untenable thing to do in practice. So here's the first example we thought of, which turned out to display this kind of behavior. And it was just for the target, we pick a k-dimensional isotropic Gaussian with unit means and variances. So the covariance matrix is identity, and the vector of means is the vector of ones. And then for the test function, we pick this thing here that just takes the product of the components of its argument. So this mu phi average just becomes, by independence, the average of each of the univariate Gaussians in this, all producted together, and each of these are 1, so the product is 1. And if you do just a little bit of calculation, you'll find that the standard deviation is square root 2 to the power k minus 1, and so the coefficient of variation is the same thing. And then if we plug this into the stuff from the slide before, we'll find that the number of samples n that we need to achieve a relative error of epsilon is grows exponentially with k. It's like 2 to the k. And this should probably be quite concerning, right? It tells us something like, if we go up 3 dimensions, we need to generate 10 times as many samples to achieve the same relative error. And you plug in some numbers and you'll see how big this can get quite quickly. Say you want a 1% error in your estimates and you're working in 20 dimensions, then you're going to have to generate about 10 to the 10 samples, which is probably going to be pushing the PCs of most people here. And if you go to 30, you need 10 to 13 samples, which is probably going to be beyond what most people's computers can do here in any sort of reasonable time. And you go a little bit further, not much, and you get beyond what we can all do collectively as humans. So this seems rather concerning. Now, at this point, you probably will start asking, okay, how can I avoid this? How can I overcome this issue? And at least for this example, in general, things like MCMC and SMC and importance sampling that we use because we cannot draw samples from most targets of interest, these are not going to save you here. They're not going to fix this problem. And there are some exceptions, and without a doubt, it's a very general statement. But in general, they won't. So for example, for MCMC, the asymptotic variance of your estimator is the asymptotic variance of the IID estimator plus the integrated autocovariance function, which then tells you that the only way of reducing variance with MCMC is making the samples the chain generates negatively correlated. And this is typically not what you're doing in practice, because most proposals involve these like local moves that make consecutive samples highly correlated. There are some exceptions. For example, using HMC in certain circumstances, you can negatively correlate the samples and decrease the variance. But in general, you're going to do the opposite. You're going to inflate the variance. And similarly, you can tell me, well, if with importance sampling, if I use a proposal that is well adapted to my integrand phi, then I can reduce the variance and I can reduce it by a lot. And yes, that's true, but it's not how we often use importance sampling these days. And also, if I switch the integrand, then you're back to square one. Right? You need to look for another proposal. Now, you're probably going to be better off by just looking at for one of the variance reduction techniques that are intended to actually solve these types of problems. So things like stratification and control variance and Rao Blackwellization. These things all have their downsides. A lot of them revolve around the fact that they can be used in special cases and not in general. And sometimes also you will have to spend a fair amount of effort trying to get them to work. But I don't really want to go too much into them more than anything else, because this particular problem has a really simple solution that just involves Monte Carlo. And I don't know, maybe a few of you have probably already guessed this. It's really simple. You start by noting that your target is the product of k univariate distributions. The integrand is the product of k scalar functions. So your average of interest is the product of the corresponding component-wise averages. And then something that might seem rather natural to do is say, okay, well, why don't I just estimate each of these things separately, right? And then take the product of these estimates and use that as an estimate for my integral of interest. And we already actually have everything we need for this, because if you look at these IID samples that we had from mu, each of them by definition is a tuple, and the components in this tuple are samples drawn from each of these marginal distributions. And on top of that, because of the product form assumption, they're independent among them. So we can then just use these component-wise samples to estimate each of these integrals. So for example, this sample mean here estimates the first of the integrals, and this one estimates the last of the integrals. We compute each of these sums, we take the product, and we use that as an estimator for mu phi. And then by the law of large numbers, if you apply it to each of these things separately, you'll immediately get that this is a consistent estimator. So if we pick n large enough, we generate enough samples, it's going to be close. So we get to the same question, how large do we need to pick n? But this time, the answer turns out to be a lot more pleasing. So with a little bit of work, you can find these expressions for the variance of this estimator. These, you can't manipulate them as easily as the other ones. They're not as simple as the IID ones, but it's pretty easy to bound them. So if you say, okay, what if I make the number of samples that I use proportional to the dimension with some proportionality constant c, then you find that the variance is bounded below by 1 divided by c and above by 1 divided by c minus 1. And then following the same steps as before, you'll find that the number of samples that you need to achieve a relative error of epsilon is bounded below by k divided by epsilon squared and above by 1 plus 1 divided by epsilon squared times k. In other words, the number of samples that you need grows linearly with k instead of exponentially, which is a much better state of affairs, right? And if you want to be safe, you can just use this number here. Then you can go to k's in the millions, and you can run this on your PC in a few seconds, and you're not going to have an issue. Okay, so the question is, fine, we've solved the problem in this very kind of trivial example. Can we do this in general in any way, or in at least a little bit more generality? And the answer is yes, and the most immediate generalization is to a generic product form measure and a generic product of univariate functions for the integrand. And then we do exactly the same. We estimate each of the component-wise averages separately with the corresponding sample average, and we take the product. And then you find that this is a consistent and unbiased estimator for mu phi. Just honestly, you spend 2 minutes on it and you'll see. Now, okay, so this generalizes a little bit, but not that much. This is still a rather special circumstance, and in particular, that you're in this trivial setting in which your average of interest decomposes into the product of several univariate averages. So can we go a little bit beyond this? And you can, and the trick is to rewrite this in a slightly different form. So you expand this product, and you'll get something like this. You'll get a 1 divided by n to the k, and then you sum over all n1s and 2s up to nk's between 1 and capital N of these corresponding products. Okay? And then as a shorthand, this thing here I can just rewrite it as phi evaluated at this, what we call a permuted tuple. So basically, it's a tuple that we've obtained by swapping component-wise around the samples of our original tuples. And by square brackets n, I just mean the numbers between 1 and n. And this thing here on the right-hand side, this makes sense regardless whether phi has any sort of product structure or not, right? And it turns out that this is a well-defined estimator for general phi as long as the target is product form. And we call it a product form estimator. It turns out that they are a special case of a generalization of U-statistics, which are typically called generalized U-statistics or multi-sample U-statistics. But I'm gonna stick with the name of product form estimator because, well, among other things, it saves me from saying ridiculous things in these kinds of talks, such as specialized generalized U-statistics and so on. But I want to leave it in non-clear terms. These things are a special case of these. You can recover most of the results I'm going to give here by specializing results previously given for these things in the literature, or at least tweaking them a little bit if necessary. Okay, so I said that these product form estimators are well defined and sensible, and what I mean by that is that if your target is product form and your integrand is square integrable, although most of these things also hold if it's integrable, then you find that the estimator is unbiased, strongly consistent, asymptotically normal. You can find expressions for its asymptotic variance and also for its finite sample variance. Now, I don't want to dwell too much on them, but I'll point out a couple of things in these expressions. For example, for the asymptotic variance, we have these sums of these terms here. And if you look at these terms, this bit here means take phi and integrate with respect to the product of all the marginals except for the one indexed by k, right? So in particular, this function here in the square brackets is a scalar function. It only depends on the kth argument. And then you integrate that against mu k. And then if you compare that with the IID estimator, in which basically here you have phi and out here you have mu, that's probably going to be better, right? In the IID estimator, we have a k-dimensional function squared integrated against mu. And by Jensen's, that's probably going to be significantly bigger than just this here that we have just a one-dimensional function squared and then integrating against mu k. And in the finite sample variance, you get something similar. It's just a little bit more complicated. You get these higher order terms, right? So instead of here being just the kth marginal, this is the product of the marginals indexed by indices inside the set B, right? So you get these higher order terms. But these are appropriately penalized by n to correspondingly higher power. I'll come back to this in a little bit. So maybe I can try to say something a little bit less wishy-washy. In our starting example, we saw that the variance was smaller for the product form estimator than for the IID estimator. You can ask, is this a fluke or can we expect it to hold in general? And the answer is you can expect it to hold in general. When you have that the variance of the product form estimator is going to be bounded above by that of the IID estimator, and the same thing holds for the asymptotic variances. And in fact, it turns out these product form estimators are the minimum variance unbiased estimators in our setting. So in other words, if I give you n IID samples from a target mu, and I tell you that the target is product form, and I ask you to produce an unbiased estimate of mu phi, the product form estimators give you the best estimate, at least in variance, in terms of variance, that you can possibly produce. Okay, so then you get into the question of how big can you expect this variance reduction to be? And the most general thing you can say about this is that you can't say anything too general. So even in you can construct very simple examples. It's just 2 dimensions. and I have some free parameter to play around with. And you can basically make the ratios of the variances, of the asymptotic variances, go to 1 by taking one limit in this free parameter, or go to infinity by taking another limit. And in other words, in this case, we have no variance reduction at all. And in this case, we have as much variance reduction as you possibly want. And by moving sigma between these two values, you can hit anything in between. So in order to say anything more detailed about the variance reduction, you're going to have to restrict the type of mu's and phi's that you have, right? And then you can hope to say something a little bit more special. These are the variance expressions for the IID estimator and for the product form one. So to gain a little bit of intuition, we can go back to our starting example. And in that case, these terms here just turned out to be 2 to the cardinality of b minus 1. So all of this is dominated basically by 2 to the power of the cardinality of a, and then that gets penalized by n to the same power. And that kind of keeps the variance in check here, while the other one here just grows exponentially, because this one is 2 to the k. And that's what we got from before. Basically, that led to the number of samples you need for the IID estimator growing exponentially with k, and for the product form estimator growing linearly with k. And then you can kind of see that what you need to get this phenomenon is this condition here. You need these terms to behave more or less like this. And if you squint at this for long enough, you can see that this is not unreasonable in a reasonably wide class of mu's and phi's. But I don't want to bang on about them too much, because it's also easy to come up with examples in which this does not hold. And consequently, you don't get this kind of behavior. So a very simple one is if phi is sum of univariate functions, then both estimators coincide, they're the same thing, and you get no variance reduction at all. And in general, if phi is a sum of low dimensional functions, I mean functions that only depend on a few of the components, right, 1, 2, or 3, something like that, then you get very little variance reduction. Both estimators perform quite closely, and there's little change. But that's okay, because these are exactly the settings in which the variance of the IID estimator doesn't grow very quickly, right? It grows like linearly or polynomially in the dimension, and so you wouldn't want to be doing anything more complicated in the first place. And then on the flip side, you can find cases in which the opposite, like you get the other kind of extreme of behavior, in which this bit here is a lot bigger than that term there, and you get, for the IID estimator, you get that the number of samples you need for a certain relative accuracy grows like super exponentially. So things like an exponential of an exponential, or something utterly terrifying. And in the case of the product form estimator, they grow also quicker. It can be polynomial in k, it can be exponential in k as well, which will tell you that it will also be limited in those problems, and those problems are just intrinsically very difficult. Now, there's one last thing I can say in some sort of generality about when you can expect this variance reduction to be big, but in order to do so, it's good if we switch our perspective a little bit. So so far we've been viewing these things here as estimators for mu phi, right? But we know from the theory that they're good estimators for mu phi for a large class of phis, right? So in reality, what we can do is just view this thing here, the empirical distribution of our original NIID samples, as an approximation to mu, right? And that's the approximation we're using here. And in the case of the product form estimator, what we're really using is we are taking each of its marginals, we're approximating it with the corresponding empirical distribution of the components of the samples, and then we're taking each of these approximations, one per marginal, and we're taking the product of them, right? And that's why we call these things product form estimators, because you're basically using a product form finite sample approximation to mu. Another way to view these is to focus on this term here, right? And what this shows is that in the case of the product form estimator, we're using the empirical distribution of all of these permuted tuples, right? So all of the tuples that we can make by permuting the components of our original n tuples. And there's n to the k, many of these, so we're dividing by 1 over n to the k. And now because mu is product form, with like almost immediately, you're going to see that each of these things has law mu. So what we end up doing is we take n IID samples we've drawn, and we permute the components, and we form n to the k other like total number of samples that all have distribution mu, without having to sample mu any further. Of course, they're not independent because we have the same component repeated across several of these permuted tuples. And for that matter, if you start from the original n and you start making permutations, the more permutations you make, the more correlations you introduce, because there are more tuples that share the same component. And this is going to be kind of important later. So here's some pictures to show what this kind of looks like in practice. This is for two targets. This is a peaked isotropic Gaussian, and this is a kind of something with fat tails. It's a product of two student heat distributions. And in both cases, we start by drawing some samples from these distributions, and then to move on to the product form estimators, we basically start permuting all the components, and we end up with a much bigger ensemble of samples, basically. And in the IID case, IID estimator, we use these empirical distributions as approximations to mu, and in the product form, we're using these things here as approximations to mu. Now, if you look at these drawings a little bit, you notice when things might work better and when they might not. So, for example, here, because the distribution is quite peaked, all the samples we've drawn are quite close to the mode. They're clumped around the mode. So by making these permutations, all we get is further samples clumped around the mode. And in particular, an average with respect to this empirical distribution is going to be quite close to an average with respect to that empirical distribution, and you're probably not going to see much difference in the variance. In this case, however, where our samples are much more spread out because the thing has fat tails, when we make permutations, we end up with a much better kind of coverage of the underlying space. And then it's not that crazy to imagine that an average with respect to these can be quite different from an average with respect to those, and hence you can see a much bigger variance reduction. And if you look at simple examples and you do a little bit of analysis, this is in fact what you'll see, that the more dispersed or spread out your target is, the greater the variance reduction that you will get by using a product form estimator. Here's an example of this analysis, and it's just an easy generalization of the example we started out with, but all I want to point out is here in the ratio of the asymptotic variances, you have the CV term that is not the same as CV as before, but basically it kind of captures how spread out the target is. So the greater this is, the bigger the dispersion, and then you see that the greater the gains in variance, and on top of it, this effect gets compounded quite drastically by the dimension. So the higher you up in dimensions, the more this is true. Okay, so at this point, this might look quite good, but you're probably thinking, okay, well, so what's the catch here? I saw someone in one of these calls a little while ago use I think it was Andy Wang, use the sentence, the physical law of conservation of hardness or of difficulty. And how does that materialize here? And it's actually really simple. For the IID estimator, all we have to do is compute this sum over the n original samples. And in this one, we have to compute a sum over n to the k samples, right? So the cost of evaluating the IID estimator is just linear in n, while in the other case, it's n to the power k, right? It's much more expensive to evaluate the product form estimator. So you can get a big variance reduction, but you're going to get a big increase in cost as well. And hence this question of which one is actually more useful in practice, which one achieves a smaller error given the same computational budget, is trickier than that of the variance. It depends on the exact target and the exact integer. And you can get some intuition by just looking at simple examples. And if you'd like to see some of that, just go to the preprint. But I'm just going to go through kind of the conclusions you get from those, because I think they're quite intuitive. The first one is that if it's, generating independent sampling the target is expensive. It's a very expensive thing. Maybe you have to run very long simulations that take days, or maybe you collect these things from experiments in real life, then the overhead of computing this bigger sum of the product form estimator probably is trivial compared to that, at which point you should use the product form estimator. Right? There's no reason not to. And basically what's happening in that setting is our samples are expensive to generate, and so we want to get the most out of them that we can, and we can do that by making permutations and artificially increasing this number of samples. Now, if this is not the case, then you got to remember that the unpermuted original samples are independent, while the permuted ones are not, and hence a new independent unpermuted tuple is worth a lot more for estimation than a new permutation. Right? And this is more and more true the more permutations you make. Right? So if you have many IID samples to start with, the first few permutations are almost going to count as in further independent samples. But if you have made a lot of permutations by now, you make another one and you have a lot of overlap with the ones that you have in your ensemble, and it gives you very little. Right? And this is the reason actually why the variance of the product form estimator is inversely proportional with n and not inversely proportional with n to the k, which is what you would see using the IID estimator with n to the k independent samples. So if samples are cheap to generate, it's cheap to sample the target, then you definitely should be using the IID estimator and not the product form one. You should spending your computational budget on generating further independent samples rather than permuting the ones you have. And there's one exception here that we already kind of saw at the beginning. In some cases, you can compute the product form estimator without having to carry out all these permutations and evaluate phi at each of them and summing them up. In particular, at the beginning, we computed the product form estimator by just computing each of the component-wise sample averages. Each of those operations are order n, and then we took the product, so the whole thing is order n. And in these cases, you should definitely use the product form one. You're going to get some variance reduction and potentially a lot, and the cost is going to be comparable. I'm going to come back to this, but before I do, I want to make one last comment. And it's this: we don't have to be so black and white. We don't have to use the n independent samples or all possible permutations we can make. We can instead make some permutations and not all of them, and then take the average with respect to whatever permutations that we've made. And we don't really have it in the preprint, like the theoretical properties of these things, but they also have everything that you want: unbiased, asymptotically normal, consistent, and all these things. And if you'd like to check that, the place to go is the literature on incomplete use statistics and their generalizations, and you can adapt those results quite a bit to this setting here. Now here the clear question is, how many permutations should I make? And the optimal number will depend on your exact target and your fee and the cost of generating samples and that kind of thing. But I think this is actually a pretty good rule of thumb. Choose the number of permutations you make such that the cost of forming these permutations and evaluating this estimator here is comparable to the cost of generating the original samples in the first place. Right? That way, if samples are very expensive to generate, you end up making a lot of permutations. If they're cheap to generate, you make few permutations. And then, kind of an obvious comment, you should try to choose these permutations to be as uncorrelated as possible. And kind of an easy way of doing that is just trying to minimize the number of overlapping entries. Okay, so on the linear cost case, right? The case where you can evaluate the product form distribution in linear amount of operations with n. Our starting situation was like this: we had mu being the product of k univariate distributions, and phi being the product of k univariate functions. And in order to evaluate the product form estimator, you just had to evaluate each of the component-wise sample averages and then take the product. And then this whole thing turned out to be order n. And of course, in this case, you want to be doing this instead of the other one. Now, this is still a very kind of special case, but you can generalize it quite easily. So if your phi is not a product of k univariate functions, but it's a sum of these products, so something like this, then the product form estimator, all you have to do to compute it is compute all the corresponding component-wise sample averages and combine them together using the sum of products you had before. And to make things a little bit less abstract, if you're working in Euclidean spaces and these are just monomials, right? I'm literally talking about polynomials here. Okay, this is still somewhat of a special case, and you have many fees that are not of this shape, right? But something that you can do is just take your fee you're interested in and approximate it with a sum of products, right? And you can do this often. So, for example, what polynomials on compact spaces are dense in the continuous functions, right? So you can approximate, sorry, in the smooth functions, you can approximate any smooth function on a compact space using polynomials, and we can do many of these things using Fourier series and whatever you like. So if you're able to construct one of these sum of product approximations that is close to your fee, so this phi j that's close to your fee, then it's not unreasonable to expect the product form estimator applied to phi being similar to that applied to phi j. And so we can just compute the latter one, which takes us order n operations, and use that as an estimator for our average. Of course, the price we pay for this lower cost is that we've introduced a bias, right? Phi j is no longer phi, so our estimator is no longer on average giving us the right thing. But if these two things are close, maybe this bias is not so big. And honestly, this is all a little bit trivial. It amounts to just dimensionality reduction. What we're doing is we're taking a high dimensional integral, mu phi, and we're approximating with the sum of products of low dimensional integrals. We estimate each of these separately, and we combine the estimates back in the same expression to get an estimate for the original average. And this, of course, is in no way new, right? If you look through the literature, in actually quite different literatures, you'll find this idea coming up. And things like mean field, going from mean field approximations in VI to stuff in stochastic mechanics from like 20, 30 years ago. Although I should say that in most of these cases, they would approximate the low dimensional integrals using either closed form expressions when they were available, and they didn't have to approximate anything, or quadrature and cubature if you were in really low dimensional spaces, these things here. I think in practice, basically a combination of these things will be the best, right? You use closed form expressions whenever you have them, quadrature if you're in 1 or 2 dimensions, something like that. Maybe you want to use something like quasi Monte Carlo for something a little bit bigger, but not too much bigger, and then otherwise Monte Carlo. Okay, so again, how does the conservation of hardness apply to this? What's the catch? Well, now we've shifted the difficulty to producing a good approximation, a good sum of products approximation to our integrand. And in our context, good means that it has small bias compared with the size of the actual average, and that it's relatively cheap to evaluate or not too expensive. Because if it's very expensive, then we kind of destroy any computational gains. And how to do this systematically is not something that we've looked into properly, I think. Of course, it's going to depend on your particular problem, but maybe for certain classes of problems, you can think of good ways of doing these approximations, and there is a huge approximation literature out there, right? And in fact, what we've been doing, which are things like Taylor expansions, are often probably about the worst thing you can do numerically, to be honest. They're not that stable. But when you can do this, it can actually be quite useful. So here's an example. This is the simplest example that we could think of to kind of try to illustrate this point. In this case, we had a product of k uniform distributions on the interval 0 to a, where a is some number greater than 1. And our integrand was basically, you take the product of the components and you raise that to you do e to the product of the components. And you can find expressions for the average of interest in terms of a hypergeometric function, but really actually what I want you guys to take away from this is how quickly this average grows with dimension. This axis is a log axis, and this is growing like an exponential of an exponential, right? So and by this, what you can tell is that this is probably going to be a hard problem. It's going to be hard to estimate this, right? So unless Jensen's inequality is very tight in this case or something, your variance is going to grow absolutely in a ridiculous way with dimension. Okay, so in this case, we can come up, it's very easy to come up with such an approximation. You take the exponential function, you take its series definition, and you truncate that at the jth plus 1 term. And then you use that as your sum of products kind of approximation. And then if we pick a large enough truncation cutoff, these two things are close. And so you can expect the product form applied to phi being close to the product form applied to this other thing. And computing this one is quite easy, right? All you have to do is you have to compute all these things here are the component-wise sample moments. And then you multiply them together and you add them all up, and you get a total cost of just order j times n times k, basically. So then the first thing you have to look at is, okay, how close are these things? In particular, how much bias am I introducing? And if you do some rough calculations, you're going to see that if you choose the cutoff to be roughly a to the k, that will keep the bias in check. So if you go underneath that, the bias will get very large. This is this thing here. The axis is the bias normalized by the actual target average. So in this case of 0.8 a to the k, it dominates after a few dimensions. And if you choose a little bit bigger than a to the k, it's going to keep it in check, and it's going to be negligible with enough dimensions. Now, this doesn't bode super well, because it seems to imply that we're going to have to grow this truncation cutoff exponentially with a dimension that is going to increase our cost exponentially, right? But this was a hard problem, so whatever we did was probably going to have difficulties at some point. But it's actually not that bad if you compare with the types of variance reductions that you can get. So this is the ratios of the asymptotic variance of the IID estimator and the product form one applied to phi j. This is the solid lines, and you see that this grows much, much quicker than the computational cost of the other one. And if you look at the standard deviations normalized by the average for the IID estimator and for the product form one, you'll see that for the IID estimator, these things get really quickly, which tells you that you're going to need a number of samples that you're not going to be able to do in practice after just a handful of dimensions. And the other one still grows quite quickly because it's a logarithmic axis, but remains viable for a much wider range of Ks. And just to show you what this looks like, here's plugging in some numbers. I chose A being 1.5 and working in 10 dimensions. So we're basically somewhere here, in which we start to see a significant difference. I'm using a cutoff of 70 and 1 million samples. And if you do, this was doing 100 repeats of the product form estimator and fitting a kernel density plot to them, this blue line, and you get something quite sensible, something close to what the CLT predicts, and also quite peaked around the actual true value. And if you looked at the mean absolute error across the repeats, you got an error of around 1%. This is what you get if you do the IID estimator, and it's just terrible, right? Well, the IID estimator mostly gives you values around 1 or very close, very low. Basically, the CLT gives you a huge variance. It's just here in the axis, you can't see it given how flat it is, and you get errors of around 100%. And if you do a little bit of calculations, you'll see that in this case, you would need something like 10 to the 18 samples for the IID estimator to give you a 1% error, which is something we can probably beyond our collective abilities, way beyond them, and for quite a while. Okay, so I think I'm going to bring it to close now, just with a couple of closing comments. And most of these are rather obvious, maybe almost embarrassingly so. But first one is that if you're trying to compute a high-dimensional integral with Monte Carlo, first, it's worth to have a think about whether the basic IID estimator would work. If you could actually literally draw independent samples from your target, would this be a viable thing? Try to get some rough bounds on the variance, because often in high-dimensional cases, it's not going to be the case. And so before you set off to do MCMC or SMC or something like that, might be worth answering this. It'll tell you whether you need to early on start investing heavily on some variance reduction techniques. Now, another kind of very generic comment, and maybe a very superficial one, but it is kind of useful. If you have some sort of independence in your problem, try to use it when you're designing an estimator for it. You're not always able to, but often you can, and it can make a significant difference. Now, an example of that is these product form estimators. Now, and I'd like to say that they are most definitely not a cure for the curse of dimensionality in Monte Carlo, but they have their time and place, and they can be, I think they're a useful tool in our belt to have, and they make certain things, certain problems solvable that otherwise they wouldn't be. I think these incomplete and linear cost variants kind of significantly expand the utility of these things. It helps you deal with this otherwise crippling end to the K cost. And this is not something I went into the talk, but it's really easy to kind of extend these things beyond just product form targets. We put some examples in our reference in the preprint. There's one for when your target is a mixture of product form distributions, and that one's kind of obvious. And also, if you're using important sampling and your proposal is product form, not your target, which probably is a lot more common, then you can do exactly the same thing. And in fact, we think that these things are going to be most useful embedded within more complicated Monte Carlo algorithms, basically to try to exploit any product structure in the problem. And this is what these generalizations of sequential Monte Carlo that I mentioned in the beginning, that's kind of what they were hoping to do. Okay, so thank you for your time. And also I'd like to thank again Francesca and Adam for all their work on this, and the EPSRC for bankrolling all of this. And yeah, if you have any questions, please do ask. I'm also in no rush, so I'm happy to stick around afterwards.